Hello everyone. I'm going to talk about magnetic reconnection inside a flux loop induced by Kelvin-Helmholtz vortices. So let me start with showing 3D peak simulations of MHD scale KH waves by Nakamura et al. And their study predicted the formation of a series of flux loops or flux transfer events of 10 dI size along the KH boundary. By flying a virtual spacecraft along this trajectory, they found large guide field reconnection signatures including parallel electron heating, little or no ion electron jets, but out-of-plane electron jets instead, and strong out-of-plane EM prime and highly localized J.E prime. And these signatures are consistent with the September 8th, 2015 MMS observations. So we found a corresponding flux transfer event that are observed by between Kelvin-Helmholtz vortices by MMS. So here the left panel shows the quasi-periodic fluctuations of field and plasma parameters including indicating Kelvin-Helmholtz vortices. We checked out the KHI condition that are satisfied, but testing that condition tells whether or not the velocity shear layer is unstable to KHI at the time of the observation, rather than the observed surface wave is a nonlinear KH wave or not. So, to confirm this point, we performed boundary normal analysis as shown by the black and magenta arrows in panel I. The black arrows are normals from the MVA analysis, and the magenta ones are normal propagation vectors calculated from full spacecraft timing. Since the typical KH waveform is steeper at the leading edges and more gentle at the trailing edges, as shown in this bottom plots, we expect that both arrows are aligned more along the x direction at the leading edges and toward y direction at the trailing edges. This is exactly what we saw in this panel I. So here the right panels show 2.5D peak simulations of a KH vortex developed along the dusk flank in panel A and in the dawn flank in panel B under northward IMF. The color coded are the electron density normalized by the initial magnetic sheath value. In both cases, the vortex-induced reconnection occurs at multiple points along the thin vortex boundary, the vortex edge layer, leading to the formation of flux loops. And their formation timescales are similar. And the scale sizes are also similar, ranging from 0.02 lambda kh, the wavelength of kh, and up to 0.1 lambda kh. Or maybe the downside ones are a bit larger, but not very different. Okay, now, so please pay attention to this sharp peak in the total pressure with a bipolar, the magnetic field component. And this indicates an FTE generated by vortex-induced reconnection, as you see in these simulations. So when I blew up this red shade here, you see a typical the M-shaped crater FTE. So I delineated the inner leading and inner trailing edges based on the local boundary normals. And please note this strong northward electron jets at the inner trailing edge, which I'm going to talk about in a minute. The outer leading and outer trailing edges were denoted by the electron flow reversal as shown in the blue profiles along the L direction. So here we speculate the in-plane geometry of the FTE as generated by vortex-induced reconnection consistent with previous simulations. So at the very center of the flux rope C, so you see the local B magnitude reduction and the out of a plane electron jets along the negative M, green arrow in panel D, and negligible the flow reversals, parallel electron heating in panel F, and positive J dot E prime, actually it is not shown here. And all these signatures strongly suggest reconnection under a large guide field. So at the inner trailing edge, so you see this strong out of a plane electron jets along the actual northward direction, or plus the M direction, and the EM prime here show an opposite behavior to our expectation. So this electron jets were not locally accelerated by this E field. So we speculate that the mid-latitude reconnection between the twisted field lines driven by Kelvin-Helmholtz vortices occurred below the MMS location, from which a strong northward jets might have been emerged as predicted by previous simulations here. So this event also demonstrates the necessity of the cross-scale studies, including the out-of-plane directional physics. So to better understand the magnetic topology of this FTE, or flux rope, we use multiple methods. So Grad-Shapranoff reconstruction indeed shows the two possible in-plane reconnection sites at the outer edges of the flux rope, and which is being compressed at the center by the two outlet jets. And also the density variations observed by MMS and the color-coded, actually here, and the color-coded onto the reconstructed field lines are consistent with the previous simulation, showing the intrusion of a high-density plasma into the magnetospheric side. But the Grad-Shapranoff assumes a 2D steady-state structure. So to see the 3D structure in the core FTE, so we used the Fuz-Sauté method. And the result shown here indicates two interlaced flux ropes. So here is our conclusion that I will simply let you read through. And this is the end of my talk. So thank you for your attention.